Good afternoon. My name is Ashlyn Foster, and I will be doing the video for our XFLR5 final project. To start off, we're going to go by declaring a couple airfoils by going to Module, Direct Foil Design, Foil, NACA airfoil. So the first one we're going to define is a 2415 as per our project guidelines for letter A. And then as well as a NACA 4412 for all of our wings that we will be declaring. So we're going to input that number, hit OK. I already have it defined, so I'm just going to go ahead and exit this out. So I have my 2415 and my 4412. Here is both of them displayed. From there, we're going to go to Module and Direct Analysis. So for this 2415, I'm not going to declare a batch analysis, as I will not be using this for the wings. So I'm just going to do a single analysis with my velocity equaling 30 meters per second from angle of attack of -5 to 20 degrees with an increment of 1 degree. So all declared by my project guidelines. So we're going to go here and we're going to click on this 2415. We're going to hit analysis, define an analysis. After calculating it out, your Reynolds number should be about 4 million to get a velocity of 30 meters per second. Hitting OK on that, it's going to pull this up with no numbers. So you're going to hit this and then you're going to hit analyze after declaring your angles of attack and increments. So now we're going to hit close on this, and this is going to pull all of your different angle of attacks at a 4 million Reynolds number. Save all of these graphs or export all of these to an Excel sheet. So export graph, save it wherever you would like. I already have mine saved, so I'm not going to save it again. But you're going to do this for all of them. Afterwards, for this 4412, I am going to define a batch analysis. So I'm going to click here, hit analysis and batch analysis, making sure that my 4412 is clicked. I'm also going to start changing these Reynolds numbers because the ones that were originally here are a little too low. So all the way down, I started at 5 million and worked my way down, going from the bottom. Declaring my angles of attack and increments, hitting analyze. I'm not going to because it takes a little bit. So I'm going to hit close. Defining that a batch analysis is going to give you something like this. It's going to give you your angles of attack for each Reynolds number that was defined. So afterwards, now that we have our batch analysis, we can go define some planes. So wing and plane design, I've already declared all mine, but I'll show you how to do the general idea of it. So you're going to hit plane and you're going to hit define a new plane. We're going to turn the elevator and the fin off. We're going to hit define, and then here is where you're going to input all of your needed numbers. So declaring your airfoils correctly, your wingspans, each one is half. Your chord lengths, your taper ratios, or your offsets, I should say, your sweep angles. Your dihedrals for our rectangle wings, we're not going to have any, for all of our wings actually, we're not going to have any dihedrals or twisting. So I'm going to go ahead and discard this since I already have my wings defined. So my wing B, which is going to be my aspect ratio of 6 with a taper ratio of 1, a rectangular wing. So our wingspan is going to be 12. Remember, this is half. Our chord lengths were given. No offsets, no dihedrals, no twist. I am going to save these. These are all saved. This one is going to be our tapered wing with an aspect ratio of 6. Here we have our half of our wingspan calculated out using the formulas in here. Taper ratio was given. Here are your platform areas that you can use to find your wingspans and your chord lengths. So all of this was done. We have an aspect ratio of 6, a wingspan of 7.8 meters, and an area of 10.14. All right, so we're going to save this, and then you're just going to do the same thing for, this is our rectangle wing with an aspect ratio of 12, and our tapered wing with an aspect ratio of 12. So kind of the same thing. After defining, here is our wingspans, chord lengths, no offset, no dihedral, no twist, airfoils. Here we go. Here's all of the other information needed. Same thing with our tapered wing. Wingspans, chord lengths calculated, no dihedrals, no twist. There is our airfoils. Okay, so after doing this, you're going to define an analysis for each wing. So here we have wing B. First, you can go to this graph. So we're going to have wing B. We're going to hit analysis, define an analysis. We're going to set our velocity to 30 meters per second as what is asked in our project guidelines, making sure our analysis is in LLT. We're going to hit save. I already have this defined, so I'm not going to. So you're going to hit this, and then you're going to come over here and you're going to declare your start angle of attack and your end angle of attack and your increment. Hit analyze, and it'll analyze it for you. It'll pull up a whole thing since I already have mine done. So here is my wing with an aspect ratio of 6, rectangular, my tapered aspect ratio 6, my rectangular aspect 12, and my tapered aspect ratio 12. So you're going to export all of these graphs just like the airfoil to Excel. And then once that is done, all of them are going to pull up in a similar format of these two. So all of these will be declared for each graph that was pulled. After doing so, I put all of them pointed in a graph. So here's all of those. Oops, wrong. So now we're gonna go. So plotted all of these. Now we're going to determine and tabulate the lift curve slopes. My partner Chloe had determined all of the lift curve slopes down here for each wing type using the CL versus angle of attack graphs and points. Tabulated those and input them into our report. Next, we needed the minimum CD, maximum CL, and maximum lift to drag ratios. So for the minimum CD, you're going to go to your CD versus angle of attack and search for your lowest number inside each of your drag coefficient values for each wing type. And that is how you will get your minimum drag coefficient. Tabulate those and put minimum CDs and what angle of attack they occur at. Same thing with maximum CL, except for opposite. You're going to go to your coefficient of lift versus angle of attack, and you're going to find your highest number in all of your wings and airfoil. Tabulate those, and same thing, maximum CL and the angle of attack they occur at. Same thing for CL, for maximum CL, you're going to do for your maximum lift to drag coefficients or maximum lift to drag ratio. So you'll go to here, your lift to drag coefficient or lift to drag ratio versus your angle of attack, and search for your highest number in your lift to drag ratios. Tabulate those and put them into here with the maximums and what angle of attack they occur at. So our zero lift drag coefficients and our K values, Chloe had calculated. So here is our, so using this, you find your zero drag coefficients, and then using your, in here, sorry. She calculated out our K values using this formula up here and using your drag coefficient at your 0 degree angle of attack. I tabulated those and put those into our report. Next we needed to declare our overall coefficients of lift, our induced drag coefficients, our induced angle of attack, effective angle of attack, and our downwash velocity. So these were calculated in this table here. Here's our induced drag using this formula, our induced angle of attack using this one, our effective angle of attack using this one, using lift and our circulation to get our downwash velocities. Tabulating those, here are our Oswald efficiencies, our wingspans, and our platform areas. And tabulating those and putting them all into our report. Next, to get your graphs, these are all of these were found at a 5-degree angle of attack. So next, using our 5-degree angle of attack, we're going to plot the variation of local lift coefficient, local induced drag coefficient, local induced angle of attack, and local downwash velocity. So in order to do these, we're going to go back to XFLR5, and in the same spot as our wing and plane designs, we're going to click this little graph over here. I'm going to take away all of these because I don't need all of them. Since we only need these at our 5 degrees, your analysis with your 30 meter per second velocity has already been defined. So we're going to go through and we're going to find our 5-degree angle of attack for each wing and show those on our graph. And we're going to go there. So next, so this is going to be your local lift coefficient. We're going to come down here and export this graph as well. I already have these exported, but you're going to do the same for the next two graphs. So we're going to go current graph, define graph settings. Here is our induced angle of attack graphs. You can reset the graphs to kind of get a better look. Save that one as well. Define graph settings, and we're going to take our induced drag coefficient as well. So we're going to export all of these and put them into Excel. Here's our induced angle of attack, our induced drag coefficients, and our local lift coefficient. So for our downwash, we're going to go to our induced angle of attack, and we're going to take this column here and we're going to turn it into radians. So for Excel, you just type in equals radians, click on the cell number, and it'll automatically turn it to radians. Next, for our downwash, we're going to take this number in radians and multiply it by 30, which is our velocity that we were looking for. And you're going to do this for each of the wings and put them in a group. Now, all of these graphs have been put into our report and shown off. So there you go with those. And then last but not least are our discussions on the effects of two parameters of the aspect ratio and taper ratio, and low speeds discussions, all produced in the bottom of our report with our references. So thank you and have a good day.